Now we have solved the first problem by ruling out all the syntactically invalid programs using grammar-based delta debugging, right? But there is still a large amount of trials and errors during the reduction. How can we make it more efficient? The solution for the next problem is to learn a policy for delta debugging using a reinforcement learning algorithm. Instead of blindly searching for minimal solutions, okay, this new algorithm guides the search, okay, based on the prediction of the learned policy. Okay. This policy can be learned from many trials and errors during the delta debugging process. Okay. And at each time, the new algorithm suggests the most likely candidate, not just following the naive order of the original delta debugging, but it suggests the most likely candidate to pass the oracle based on the learned policy. Okay. And also note that this new algorithm based on the policy does not fundamentally change the searching strategy of the original delta debugging. Okay, it just prioritizes the candidates made by the original delta debugging based on the probability. Okay, so the worst case time complexity will be the same as before. Okay. Here I show you the effectiveness of the new reduction algorithm, okay, for a Linux program called mkdir. Okay. This graph shows the overall performance of the two different algorithms, okay, the guided search and unguided search. Guided means the guided search by learned policy, and unguided means just using the grammar-based delta debugging. Okay. As you can see, this guided search, okay, can quickly find a one minimal solution within here about 1500 iterations, right? But this unguided search, you can find it after around 5000 iterations. So you can see the difference for effectiveness. So here is a more concrete example. The shaded part is actually unnecessary for the desired functionalities for this particular experiment. Okay. So both of the delta debugging algorithm, okay, the guided and unguided delta debugging algorithm, eventually remove the shaded part. Okay. Then a minimal program only contains the unshaded part. Okay. Only this orange part. The learning guide. So first let me explain how the unguided delta debugging works. This unguided delta debugging first divides the whole program, okay, which contains 13 elements, into two parts, as you already know. Okay, and try to check each part satisfies the oracle or not. But the answer will be no, because each of them misses some important part, right? This one misses some important part 8 and 12, 13, and this one misses 1 series, and so on. Okay. Then it will do the same job with more finer granularity recursively. It tries to check whether the vector with 1, 2, 3, 4, okay, will pass the oracle, and it will try the complement, and so on and so forth. Okay. But it cannot find the first successful case, which is a superset of the desired program, okay, until 16 iterations. Okay. After 16 iterations, as you can see, it tries this program, okay, that is a superset of this guy. Okay. Then it passed the oracle. Okay. And then it keep doing this, okay, with this program, okay, again and again. And finally, it can find the minimal program after 65 iterations. Okay. And then next, let's see how the guided delta debugging works. At first, the guided version makes the same mistakes like this. the first hop does not satisfy the oracle. But the difference here is that over time, the new system learns a policy from this kind of trials and errors. The idea is simple. The system simply encodes each candidate program as Boolean vector like this. Each part, okay, if each part is included, then we'll assign 1 here. Okay, not included, 0. Okay, you can construct a feature vector in this way. And then the system labels the data based on the feedback from this oracle. Okay. Then with this data, okay, the new system can learn a decision tree. So from now on, the search is guided by this decision tree. Okay. So according to the original delta debugging process, what is the immediate next candidate? Okay, the immediate next candidate is this one, right? The second hop. But see if this second hop satisfies the decision tree. Right? The answer is no, right? Because the decision tree suggests the minimal program should include label 6 and 12, but the second hop, okay, does not satisfy this condition. Okay. So the algorithm keeps trying the second hop that does not satisfy the decision tree. And then instead it directly get into a final granularity, and find the next candidate that follows the decision tree's guidance. Okay, this one that satisfies the decision tree's guidance. But unfortunately, it still fails. Okay. In this case, the system again add this case to the data set and build another decision tree. As you can see, the decision tree has been updated, okay, refined over time. And keep doing the same process and search under the guidance from the decision tree. Then after only 7 iterations, it can find the first successful candidate. That is actually the same program the unguided version could find after 16 iterations. Okay. And then finally it can find the minimal solution, okay, only after 13 iterations. Okay. In total, more than 4 times less trials. So that is how the system efficiently search for a minimal program. Then the last research question is how to validate robustness of the reduced program. So here, the Chisel system checks the robustness of the reduced program to prevent newly introduced security holes by the reduction. It will use static and dynamic analysis. So the validation process first runs a sound static analyzer, okay, especially for this case, a sound static buffer overrun analyzer. So as you can see, after the reduction, because of the size reduction, the static analyzer also reports only a very small number of alarms, okay, which are far less than the number of alarms in the original version. That makes it feasible to inspect all of them manually. Okay. And also for each reduced program, it runs a fuzzer, which is a random testing tool, for a long time and see if it finds a new bug. Okay. During the validation process, when the fuzzer finds a new crashing input, then the system can simply augment the test script with the newly found counterexample. For example, in the initial test script for GNU grab, okay, the GNU grab was not tested with very long input, larger than the initial automata size. So Chisel just removed this reallocation process. But as you can see, this part can be easily restored when the system the chisel system augment the test script with this newly found input by the fuzzer. Here is the experimental setup from the paper. 10 widely used Unix utility programs are used for the experiment. Okay. Each program has a known CVE or security vulnerabilities. And also for fair comparison, a static analysis first removes all unreachable code upfront. Okay. And the specification is described as follows. The reduced program supports the same command line options as BitBox, and the behavior is checked with the test suite by the original developers. So let's first compare the size of the reduced program by chisel with the original version, okay, and manually reduced version from BitBox. First of all, the original programs have 55,000 C statements. Okay. Among them, chisel could reduce 89% of the code. Okay. These results are comparable to handwritten version. Okay. Next, let's see how chisel can improve the security. Okay. First, we can see whether CVEs, security vulnerabilities, are removed or not. For 6 programs out of 10, chisel could remove the security vulnerabilities. Okay. Among them, 4 are from undesired features and 2 are even from desired functionalities. Okay. And the remaining 4, okay, are not easily fixable by just removing the code. For example, race condition is not easily fixable by removing some piece of code. Okay. And next, okay, the chisel can reduce the 66% of ROP gadget. Okay. Here, gadget means a small piece of code in binary code, okay, that can be used by code reuse attack. So in principle, less gadget means more secure. Okay. Also, after the reduction, the static analyzer report 95% less alarms. So it make it feasible for manual alarm inspection for reduced program. Next, let's compare the performance of chisel against the existing program reduction tools. First, C-reduce, which is based on the naive delta debugging algorithm. This one ran out of time for 6 programs out of 10 because it makes a lot of syntactically and semantically invalid programs during the reduction steps. Next is persist, that is a grammar-based reducer that rules out a lot of syntactically invalid candidates, but still ran out of time for 2 programs because of a lot of semantically invalid candidates. But chisel could reduce all the programs within 12 hours, okay, and 7 times and 4 times faster than the baseline reducers, respectively. Okay, let me summarize this lecture. We have learned a technique called program debloating that simplifies and hardens large and complex software. One example is the chisel system, okay, which is doing tractable search using learning guided delta debugging and security hardening by removing undesired features. The robustness of the reduced code can be checked using static and dynamic analysis. This is a still very new research area, so it requires a lot more research on efficiency and effectiveness. For example, more advanced learning techniques and system level debloating. For example, inter-program debloating and so on. Okay, that is the program debloating.